Hey Phys Kids, Campbell here. In our last video on momentum, we're going to talk about angular momentum. Now, we've spent all this time talking about linear momentum, momentum being mass times velocity, but remember that every linear variable has a rotational variable, and so the rotational equivalent to linear momentum is angular momentum, symbolized by an L. Now, if we think about an object moving, like say this golf ball, all right, this golf ball, if it's moving, has a momentum m times v. But all angular quantities, remember, are different from their linear quantities by including an r, a distance measured from some reference point. So let's say I have this golf ball moving with some linear momentum. I could calculate its angular momentum, even though it doesn't look like it's moving in a circle. I could calculate its angular momentum by taking the mass times the velocity, so my linear momentum, and multiplying by the distance from that reference point. So the angular momentum, L, is mass times velocity, our linear momentum component, times r, the distance from some reference point. Usually it's a point of pivot, times the sine of theta. Now we need to use the sine of theta just like with torque. When we had torque, remember, we wanted that component that was perpendicular to the lever arm. And in this case, if we draw a line through from the reference point through the mass, and we want that velocity vector that's perpendicular to that line that we drew. And so that usually is the sine of theta, just like with torque. It was always pretty much the sine of theta. Now, I know it seems weird to talk about the angular momentum of an object that's just moving in a straight line. Usually you would think about maybe if I just swung this guy on a string, right, and I made it go in circles. Well, now that seems more logical for an angular momentum, and r would be the distance from where it's pivoting. So, but anything that has linear momentum has an angular momentum. It just might be changing all the time. Now, if we think about rigid objects, so for example, if I look at this wheel here, a bike wheel, so when I rotate this, right, every particle on this rotating wheel has a velocity which is different, right, depending upon the distance from the center of rotation. But every point on here, every piece of mass on this wheel is rotating with the same angular velocity. So if we take that angular velocity equation that we had for our little point mass, that golf ball, and instead of v, here we substitute in the rotational equivalent omega times r, I now have this, and if we distribute the r, we end up with mr squared times omega. Now, mr squared, does that look like anything familiar? Well, remember that moment of inertia is the sum of the mr squares, and so for a disk, remember that the rotational inertia of a disk was 1/2 mr squared. So we're going to need those rotational inertia values for our rigid objects again. Remember, a hoop was mr squared, a sphere I think was like 2/5 mr squared. So when we have a rigid object, instead of using mr squared times omega, we'll use the moment of inertia I times the angular velocity. Now, direction is important in angular momentum. Just remember when we talked about torque, how I said the direction of torque you could figure out by using the right hand rule. So if you take your right hand and you had your fingers move in the direction the object was accelerating, the torque was the direction your thumb was pointing. The same thing is true when we talk about angular velocity and angular momentum. Angular momentum is always in the direction of the angular velocity, just like momentum, linear momentum, was always in the direction of the linear velocity. Well, so if we take our right hand and we wrap our fingers so that they are moving in the direction that the object is rotating, if it's rotating in this direction and my thumb's up, that means the angular velocity and the angular momentum are up. And if instead it's rotating in the opposite direction, so that would actually be clockwise, then my thumb is down, so that means the angular velocity and the angular momentum is down. Now, the link between linear and angular momentum, right? I mean, yeah, it's mass times velocity, and with angular, we have a r value in there. But if you think about objects that are rotating, because masses are distributed, masses that are closer to the point of rotation have a smaller velocity than those way out on the edge, which have a bigger velocity. So objects on a rotating rigid object have different linear momentums, but the same angular momentums. So it's much more appropriate to talk about the angular momentum of an object. Now, if we go back to linear momentum, we think about the impulse momentum theorem, right? That comes from Newton's second law and kinematics. And so we had that force times time, impulse, is equal to a change in momentum. Well, we have that same thing for angular impulse and angular momentum. So for rotational motion, instead of talking about force, right, we talk about torque being force times distance. And remember that torque, the sum of the torques is equal to I alpha, the rotational inertia, times the angular acceleration. Well, we can do the same thing with that impulse momentum theorem. We could take torque times time, and torque times time is equal to the change in angular momentum. So impulse, force times time, is equal to a change in linear momentum. Torque times time is equal to a change in angular momentum. Now, if we talk about torque and the rate of change of angular momentum, right? If there is a net torque, an object's going to accelerate. Now, if the torque is parallel to the angular velocity, then it changes its angular velocity. So it speeds up or slows down the system. So for example, I have this rotating wheel here, and I apply a torque parallel to the angular momentum. So my torque is up and my angular momentum's up. Then my object speeds up. Or if I go in the opposite direction, right, it will slow down until it stops. So torque parallel to the angular momentum causes a change in angular velocity, but a torque perpendicular, so if I try to rotate this wheel, torque perpendicular to the angular momentum causes a direction change in the angular momentum. Now, we're going to actually play around with this because trying to rotate this thing this way is actually very difficult. And that's because an object wants to conserve its angular momentum. So when I apply a torque parallel, it'll speed up or slow down. If I try to apply a torque perpendicular, it's going to change its direction without changing its angular momentum. Just like linear momentum, objects conserve angular momentum, and that the angular momentum before is equal to the angular momentum after if there is no net torque. So if I'm not trying to change the direction or if I'm not trying to change the speed. Now, what this means is that if I change the radius of an object, it's going to change the speed of an object. Think about an ice skater. When you see ice skaters skating, right, if they're spinning in circles, sometimes they'll have their arms out, and then they'll pull them in tight, and they'll start to speed up. They do that because if angular momentum is conserved and they're spinning, right here with their arms out, they have a high rotational inertia, and by just bringing their arms in, they decrease their rotational inertia, which will therefore increase speed. So by the law of conservation of rotational inertia, if there is no net torque on the system, then the initial angular momentum must equal the final angular momentum. The initial angular momentum would be that rotational inertia initial times that angular velocity initial equal to the final rotational inertia times the final angular velocity. So if I'm spinning with my arms out initially, and I pull my arms in, that means my rotational inertia goes down. Therefore, my rotational speed or my angular velocity has to increase because they have to equal a constant value. So ice skating is a classic example of conservation of angular momentum. Another good example is the rotation of planets around the sun. Now, this is a little bit of an exaggerated drawing of our elliptical orbit with the sun, but we rotate around the sun and we do have a slightly elliptical orbit. And so that means is as we get closer to the sun, as we go through this orbit here, right, when I get here, my radius, that orbital radius is much closer than when I'm out here. And angular momentum is conserved, so what that means is that when I have a small radius, like in here, then I'm going to have a higher speed. So small radius means I'm going to have a higher speed, linear velocity or angular velocity. And as I get farther away from the sun, then my radius gets bigger, so that goes up, and my speed gets slower. So orbiting planets is another great application of the conservation of angular momentum. Last thing I want to talk about, we have a figure here with two masses that are currently held together by a thread. So I have these two masses here and they're connected by a thread, and this rod here is rotating at a constant angular velocity. Now, if the thread breaks, right, that means that these things are going to go to the outer edges, right? They no longer have a centripetal force by the thread keeping it towards the center, so they're going to roll out here till this applies a force keeping them in the circle. Oops, sorry. So if those go out farther, what happens to the angular momentum? Well, nothing, right? Conservation of angular momentum, as long as I don't apply a torque to the system and there's no friction, it's just going to keep rotating with constant angular momentum. But when these masses go out, then I've increased my I. So my rotational inertia went up, so that means that my angular speed must decrease. Angular momentum is a constant in the absence of an external torque. All right, we got some more stuff to talk about in class, and I want you to spin this wheel, so I'll see you in class.